No, maybe pick a new one. Good afternoon. So now we will illustrate the results we saw with Cobb-Douglas utility functions and Leontief utility functions. So first, Cobb-Douglas. All the coefficients are positive. And then we have to solve the utility maximization problem for this utility function. By the way, this is a nice utility function because it's always quasi-concave. Even concave with the sum of the alphas is less than or equal to 1. But in general, quasi-concave. It's also non-decreasing and continuous. So it's very nice. And then we are going to solve the problem of maximizing A pi subject to the budget constraint. Okay. Then we first consider a trivial case. Now we have to distinguish because in producer theory, prices were always strictly positive. Now they are allowed to be zero, some prices. Okay, so I first consider the case when P is not in the strictly positive orthon. So P is non-negative always, but it may have some zero component now. Then the optimal value of this problem which is V of P, V being the indirect utility function. What is V of P in this case? I mean, what is the optimal value of this problem if some Pi is equal to 0? What did you say? So if some Pi is equal to 0, then for the remaining i's you can take some amount of xi which satisfies the constraint, just a small amount. I mean, even 0. Okay, so suppose Pi is 0. Then for j different from for I, you take xj equals 0 and xi arbitrary, any xi. Then this sum would be 0. But don't take a j equals 0. Can take x small enough. Small enough so that the sum of pj is xj, which is the sum of j different from I, because pi is 0, of pj xj is less than or equal to 1. Okay, you can always find x small enough, even strictly less, because for 0 it gives 0, then by continuity you can take a positive number, the same for all components. Then for this xj, when you make that particular xi sufficiently large, going to plus infinity, this goes to plus infinity. Okay? In economic terms, if good I is for free, my demand of good I can be as large as I want without violating the budget constraint, and then my utility goes to plus infinity. Okay? So this is, for this case, the solution to the optimization problem is trivial. The optimal value is plus infinity. Do you agree? Then consider the interesting case, which is when P is in R plus plus N. All components or P are strictly positive. Then let us solve this problem by considering the Lagrangian function associated to it. I use the format for the Lagrangian of a minimization problem, so I change the sign of the objective function. I prefer it. And I apply the KKT theorem, but not your version, because your version was for convex problems. And this is not necessarily convex. Well, this would be convex when the sum of the alpha i's is less than or equal to 1, but we are in the general case now. But anyway, as a necessary condition, the KKT theorem also holds for differentiable functions, even in the non-convex case. As long as the some regularity condition holds. I think you didn't mention yesterday any regularity condition because you were only considering Fritz-John condition, but you probably, because you are in convexity, you will tell us about the Slater condition, which is very simple. Here is not the Slater, but here is the linear independence constraint qualification, which in the case of just one constraint means that the gradient does not vanish. And of course, the gradient of this function never vanishes, the positive orthant. So we can apply the KKT theorem to obtain that at an optimal solution, the gradient of the Lagrangian with respect to x vanishes, then we have non-negativity of the multiplier plus the complementarity condition. So let us write, so the partial derivative of the Lagrangian function with respect to x is what? If we take derivatives here, then for the jth factor here, we will get alpha I, and then xj to the power alpha j minus 1. I keep xj to the power alpha j in this factor, then the minus 1 implies that we have to divide by xj. But then, since I have kept xj to the power alpha j here, what I get, I forgot the minus sign, what I get is this expression, which is u of x, okay? U of x1 xn. divided by, sorry, this is alpha j, divided by xj. Do you agree? Plus lambda pj. So the KKT conditions are minus alpha j u of x divided by xj plus lambda pj equal to 0 for j from 1 to n, lambda non-negative, and lambda times the sum of pi xi minus 1 equal to 0, plus the constraints, the only constraint we have. Then, as usually happens to us, lambda cannot be 0, because if lambda were 0, this inequality would tell us that alpha j is 0, which is not the case, or u of x is 0, which is not the case either. Well, but we are dividing by xj. Do we have the right to divide by xj? Is xj different from 0? Certainly, because we are dealing with an optimal solution, and at an optimal solution, no xj can be equal to 0. This can be easily seen. Okay, then, so lambda is strictly positive. This means that the constraint is active. Now from this equation we obtain xj. I mean, was it clear what I said, that xj, the reason why xj is different from 0? Because it's optimal. It makes part of an optimal solution. And if some xj is equal to 0, the objective function takes the value 0, which is not optimal in any case. Okay? Well then, xj is alpha j u of x divided by pj. Now it's licit to divide by pj because we are dealing with strictly positive prices. Now we are going to use this condition. If we move pj to the left-hand side and add over j, we get this sum. And on the right-hand side, we get u of x times the sum of the alpha j's, which I call alpha as usual. So the conclusion is alpha u of x I forgot this lambda. Okay? When I solve this equation, I forgot to divide by lambda. So now it's alpha u of x divided by lambda is equal to 1. So u of x divided by lambda is 1 into alpha. Let's come again to this equality. So this means that xj is alpha j into pj times u of x over lambda, which is 1 over alpha. So this gives us alpha j divided by alpha pj. This is the optimal solution. This is our demand for goods, for good j. Then if we replace it into the definition of the Cobb-Douglas function, then we get that V of P which is u of that optimal x with this xj is A times the product over I of alpha j divided by alpha times pj to the power alpha I. Which I can rewrite as A times alpha, it's multiplied by alpha I, and then the product would have the sum as the exponent, but it's on the denominator, so it will come out with a minus exponent. So it's alpha to the power minus alpha. Then I also have, well, the subindex is wrong because here I have xi and I use the expression for xa, but I forgot to change the subindex. Now it is correct. And so I get also the product of, I prefer to write the product over I of alpha I to the power alpha I. So these are all the constants appearing here. And then the variables, which are I, is the product of pi, which is in the denominator, to the power minus alpha I. So this is the expression of the indirect utility function in the Cobb-Douglas case. It is not Cobb-Douglas, but it looks like. I mean, it could not be Cobb-Douglas because Cobb-Douglas are non-decreasing and this should be non-increasing. But the difference is in the minus sign. So you get a constant here times a product of the variables raised to an exponent, but these exponents are now negative. In the Cobb-Douglas case, they were positive. It's very easy to check that this indirect utility function is as it should be, as every indirect utility function is. Quasi-convex, non-increasing, and lower semi-continuous. It is even continuous. Well, on the positive orthan, but strictly positive, but also everywhere, because when we move to the border, to the boundary, this goes to plus infinity. Okay, so it's a continuous function. Now, because Cobb-Douglas are regular, we know that if we apply our formula to obtain a utility function inducing this indirect utility function, then we will get the original one. by regularity of the original one. Okay? Let us going to check that. So our formula was infimum for given x our formula for what we call U0, U0, was the infimum of V of p subject to px less than or equal to 1. P is non-negative. For this infimum, I can add the constraint that P is strictly positive. In principle, it is not. But if I impose this extra condition, the optimal value does not change, because the p's I am excluding, but by imposing this constraint, are not candidates for the infimum, because V of p is plus infinity for those p's. Okay? So I can impose these extra constraints, which allows me to use this expression from the indirect utility function, which is valid only on the positive ortho. Okay? So what I have to do is to minimize, to find the infimum of that expression. Let me call this constant k, for instance. Now x is given and pi's are the variables. This is a very similar problem to the one we solved to compute the indirect utility function. So if I was able to solve the problem that time, I am supposed to be able to solve the problem now. It's very similar. But I am too lazy to solve a similar optimization problem again. And also I make many mistakes when making these computations, so I want to avoid it. Do you think any way to avoid it, to obtain the infimum of this function over that constraint set? The idea is that, okay, this is a positive valued function. The idea is that minimizing a positive valued function is equivalent to maximizing its reciprocal. Okay? So if you want to minimize f of x, and f of x is positive everywhere, then you equivalent maximize the reciprocal. And then once you do that, then you invert again. You take the reciprocal. Okay? This is what I am going to do. This will save me using again the KKT theorem to do the same exercise, basically. So what I am writing is that I will take infimum. I will replace infimum with supremum. But then I have to take the reciprocal of the objective function. So it would be 1 over k the product of pi to the power alpha I, because it's the reciprocal now, subject to this constraint, and then after I obtain this supremum, I have to take the reciprocal again. Okay? So I'm using the fact that under this condition, the infimum of f of x over some set C is the supremum of f of x to the minus 1 over the same set, and then to the minus 1. This is what I am using. But this is fantastic, because now this is a genuine Cobb-Douglas function, a positive function, positive exponents, k minus 1 is also positive, and the same constraint. Now it's over p. Then it was over x, but there is symmetry. So I have already solved this problem. Okay? With a times the product of xi to the power alpha I, but it has exactly the same structure. So I already know the solution. The solution is what I obtained for the indirect utility function. So now, let's be careful. K to the minus 1 plays the role of A in the direct computation. Okay? So first of all, I have to distinguish two cases. If x is not strictly positive, then we know, because we already made this comment when computing the indirect utility function, then we know, we obtain that this supremum is plus infinity. Okay, if some component of x is 0, we saw it when some component of p is 0, then v of p was plus infinity. Now this is plus infinity if some component of x is 0. But then we take the inverse. 1 over plus infinity is 0. So this case is done. But now, if x is strictly positive, then what we get is we have to make some computation. When we had A, for the supremum, we got A multiplied with this. When A is replaced with k minus 1, what we obtain is k minus 1 times all that. But if you look at the definition of k, this is simply a to the minus 1. Do you agree? So here what we get is a minus 1. I mean, all this constant in our case reduces to a to the minus 1. And then what else? This product. But now with xi instead of pi. And this is to the minus 1, to the power minus 1. So what I really get is a times the product over I of xi over alpha I, which is our Cobb-Douglas. In fact, in both cases, because the Cobb-Douglas assigns the value 0 to a vector which is not strictly positive. Okay? So, the utility function I deduce from your indirect utility function coincides with your original utility function, not by accident, but because your utility function is regular, is quasi-concave, non-decreasing, and continuous. Upper semi-continuous should be enough. Was this clear? So now let us consider our other classical example, which is Leontief. So this is the minimum over I of xi over ai for ai positive. It also makes sense as a utility function. In the case of producer theory, the example I gave you to motivate this definition was about producing a fertilizer using some chemical products. Now suppose instead of a fertilizer you want to cook some food, and the fertilizers are the ingredients now. Okay, and then the utility you get is the amount of food you can produce out of the given amounts of ingredients you have. Then the same idea applies. Then this would be, so if you need AI units of good I, of the ingredient I, to produce 1 unit of your food, of the food you want to cook, and the amounts of the ingredients you have are x1, xn, then this is the amount of food you will be able to cook. And this gives you the utility. I mean, it represents your preferences, because your preference is the more food you can produce, the better you are. Okay? So this represents your preferences. So it makes sense also in consumer theory. So let us solve the consumer utility maximization problem for this particular utility function. So we have to maximize this utility function subject to the budget constraint forget KKT, because this is not differentiable. We could use your KKT because this is convex, but things can be made simpler. I claim that at the optimal solution, Well, first of all, as usual, if P is not strictly positive, if some good is free, my demand for that good would be, let's say, infinity, and then I can get a utility equal to plus infinity. I mean, I can get as much as possible, okay? Because I keep the remaining goods at a small amount in order to satisfy the budget constraint, and then this zero component, I can take xi large enough with it violating is, and then this will go to plus infinity. Okay. So if now, in fact, in this case, what I would do, no, it's not so obvious now, if I think it more carefully. It's not so obvious, it's true. But not so obvious, because we are taking here the minimum. And then, no, this is not what I need. No, I don't need to distinguish between being non-strictly positive or not. The only distinction that is in order now is P being equal to 0 or P being different from 0. Then it is when P is equal to 0 when V of P is plus infinity. So let's say simply V of 0 is plus infinity. This is clear because if P is 0, this constraint doesn't impose any restriction, so I can take whatever x, and then the objective function can be made as large as possible, so it goes to plus infinity. It was not true what I previously said. Now, if P is different from 0, then I claim that there is an optimal solution, and for this optimal solution, all these terms in the minimum are necessarily the same. Do you agree with that? I mean, so I can't restrict my attention to points for which all the xi over I are the same. Suppose you give me one point in which they are not all the same. I will provide you with a better point. Better in the sense that the objective function value is larger. We are maximizing, and still my new solution will satisfy your constraint. The idea, if you don't agree or don't understand my way of telling the idea, is that if for some xi, if some xi is less than what it should be to have the equality, then I can buy less of another xi and spend the money I save on that one, which was smaller, and this should maximize the minimum. But maybe this is not very clear, so let me try to give you the details. Okay? Suppose we have, for some solution, let's say x1, in order not to introduce appendices, x1 over a1 is less than x2 over a2. I don't care what happens with the other xi. Then I will find a better solution than this one by simply changing the values of x1 and the values of x2. The constraint says that p1x1 plus p2x2 plus the sum of the remaining pixi is less than or equal to 1. But then I can find x prime 1 and x prime 2 such that this does not change. These are the only values I change in x. These ones, I keep them the same. But x prime 1 over a1 is greater than x1 over a1. And assume that x1 over a1 was the minimum. Then the minimum will have increased. We can make this computation. So what do we need? X prime 1 greater than x1, simply. Okay? So, if you take some epsilon small enough, and you take x1 plus epsilon, and I need p1 x1 plus epsilon plus p2 x2 prime equal p1 x1 plus p2 x2. This is what I want. Then what is x2 prime? x2 prime should be equal to x2 minus p1 over p2 epsilon. Is this correct? So what I am saying is that P1 H1 plus epsilon plus P2 X2 minus P1 over P2 epsilon plus the sum of the remaining PIs is still equal to 1, because it's the same as it was initially. So then it is less than or equal to 1, because what I have added is this term here and this term here which cancel out. And then x1 plus epsilon A1 is greater than it was before. I have added epsilon, but it will be still less than the remaining xi over ei if epsilon is small enough, because this inequality was true for epsilon equals 0. So we have a finite number of conditions here, then we can find such an epsilon. Is now more clear what I said? Economically, it's very intuitive. If you want to cook that food, you don't need to have too much of any of its ingredients. So the bound that imposes of the amount of food that you can produce should be the same for all the ingredients. If for some ingredient is larger, then this means you have useless amount of that ingredient. That's the idea. So I don't know if this argument was clear enough, but let us hope it was. So this means we have x1. We can restrict our attention to the case when all these ratios are the same. So we have that u of x, which is the minimum of all of them, is each of them. So this is telling us that xi should be equal to ai times u of x. Something which is also obvious is that the constraint should be active at an optimal point. Okay, because if at an optimal point you have a strict inequality, then you still have money to buy more, and then you buy a little bit of each ingredient, and then the minimum would increase. Okay, or you spend all the extra money in the smallest, whatever you want. Okay, so there is no loss of generality in assuming that the sum of pi xi is equal to 1. And if you replace but what we have obtained, then what you get is that u of x times the sum of pi x ai is equal to 1. So u of x is equal to, or let us simply write inner product pi times u of x equal to 1. Now, what can we say of V of P, which is the optimal solution of that problem? We already know that it is plus infinity if p is 0. So we are now considering the case when p is strictly positive. Not strictly positive, different from 0. It's different from 0 but not negative. So when multiplied with a strictly positive vector, this product is strictly positive. So we can say that u of x in this case is equal to 1 over p times a. We are not dividing by 0. Okay. So this is the expression for v of p. 0 if p is equal to 0, and plus infinity if p is equal to 0, and 1 over pa if p is different from 0. This is the indirect utility function corresponding to your Leontief production function, which also makes a lot of sense from an economic point of view. When you have to choose among different supermarkets, what do you care? You care the amount of food you will be able to produce. So you will buy the ingredients in the proportions that are required to produce 1 unit of food. This is what this condition is saying. Okay? So the optimal input or the optimal good is proportional to the proportion of that good that enters into your recipe. And now, so you will care in how much you have to pay to be able to produce 1 unit of your food. 1 unit of your food requires I of each ingredient, so the vector I. So this is the cost of producing 1 unit of your food. So you care about the reciprocal. Okay? I mean, you prefer a supermarket in which this cost is lower, so in which this quotient is higher. So the higher V of P, the better P for you, the better supermarket. Is this explanation clear? But now, so in fact the solution here is, the optimal solution is more clear if we use this there. So if we write xi equal ai over pa. Okay? This is the demand corresponding to these prices. Well, but now the Leontief production function is very nice. It's concave, quasi-concavity would be enough, is non-decreasing, and is continuous. Upper continuity would be enough. Then, according to the theorem we saw, we should be able to recover it by using our formula from the indirect utility function. Let's try to see if this is the case or not. So our function u0 was given by the infimum of v of p subject to px less than or equal to 1. Of course, if we are minimizing, we don't need to consider the points for which the objective function is plus infinity. Okay, so I don't need to consider p equals 0. And imposing these extra constraints allows me to use the expression we just found for the indirect utility function we obtained. So this is the infimum of 1 over PA subject to Px is less than or equal to 1 P is different from 0 . Here we could use whatever version of KKT, the differentiable version or even the convex version by applying some trick, but there is no need. There is no need because, first of all, for the optimal P, we would have equality here. Because if it is satisfied strictly, I can increase P so that this is still satisfied, and this denominator will increase, which means that the objective function will decrease. Okay? So if the inequality is satisfied non-strictly, then it cannot be optimal. So I impose the extra constraint that Px is equal to 1, and nothing changes. And I'm very happy with this constraint because this means that we are on a compact set. Be careful because X may have some 0 component. I don't believe this may happen. No, I mean, I have to distinguish two cases. If X is not strictly positive, then some component is 0. For that component, I can take the corresponding PI as large as possible without violating this constraint, and this denominator would go to plus infinity, which means the quotient would go to 0. So if this is not strictly positive, then U0 of X would be plus infinity, which is surprising to me. No, it's 0. I said, I can take that component of P as large as possible, which would make the denominator not go to 0, but to go to plus infinity. So the quotient would tend to 0. Then it's not surprising at all. So, and of course, this is the value that the Leontief utility function takes in this case, because the minimum would be attained at that xi which is equal to 0. Okay? But now let us consider the more interesting case in which x has all of its components positive. Now it's when I am very happy, because we are on a compact set. Actually, a compact polytope. So is okay in general, because xpi is non-negative and is also less than or equal to over xi. Now xi is strictly positive. Okay? So the variables are bounded and the set is closed. This is a polytope of this type. And minimizing this function is equivalent, as we already observed, to maximizing its reciprocal. And so if I want to maximize this linear function over this convex polytope, I just need to consider the vertices. So this would be the minimum, for the denominator the maximum, of 1 over, which are the vertices of this polytope. The vertices are obtained when all the variables except 1, because there is only one equality, are equal to 0. So here I am describing the vertices. So the vertices are of the type 1 over xi, ei being the unit vector, the ith unit vector, as usual. So I have to compare 1 over p, 1 over xi, 1 over x1, this is a comma, 1 over x1 e1, one over p, 1 over xn, en. And this is the minimum over I of 1 over p ei is the ith component. Where is the mistake? Yeah. That the mistake is that P are the vertices. A is the coefficient of the objective function. So I am considering just vertices, but vertices are the values of P. Okay, so it's 1 over 1 over xi or x1 e1 times a, 1 over xn en a. So it's the minimum over I of 1 over EI times A is the ith component of A, which we call AI, and then divided by Xi. So we get the minimum over I of Xi divided by Xi, AI, which is our Leontief production function. Okay, so we check by means of this second example that our theorem holds true whenever the original function is regular enough. So I think it's time to stop, and then on Monday we will start talking about demand correspondences, demand functions, and in particular we will see that the demand may be surprising in the sense that sometimes we go to the market, we see that the price of some good has increased, and then we say, okay, no, I'm going to buy more of this good. You don't need to be crazy to do that. You will see what. And this is not because of what you said, that, okay, the price is higher, then if I buy it and people will see me dressing so fancy, my prestige will increase. This does not fit into this model, because this should mean that your preferences involve prices. Your utility function depends on prices, but your utility function depends only on commodity bundles. Prices are not an argument in your utility function. They don't enter into your preferences. So this is a different phenomenon which can be analyzed differently, but not by this model. Okay? Okay, thank you. Any question or comment? Or good. Now it's your turn.